this data query API that I built at Domo. We're not going to look at the exact same one I built, but basically how I built that one, because it solved a real problem that we had, which was we had our internal database that all of our services were using to build our product, and we actually wanted to expose some of this to the user. But we ran into a problem, which was that our API that we had been using internally was kind of complicated and not really very fun to use, not user-friendly. And it was actually kind of dangerous, too. I don't know if you've heard of the Little Bobby Tables joke from XKCD. We really didn't want to actually give access to our users to this API. So it was useful on its own, for how we were using it internally. It was a great API, just not really fit as a public API. So what we needed was something to kind of sandwich in between the user and that API that would abstract that interface, implement like a subset of its features, and make our users actually happy using it. So what I'm going to talk about today, in building that, some of the concepts we'll go over is writing a grammar, using Scala's RegexParsers, and abstract syntax trees. And so this is kind of the flow of how this solution is designed. Is you have a query string coming in on your HTTP request from the user, and your regex parsers will filter that out, or will parse it, and then it'll attach it to an abstract syntax tree so you can semantically interpret that data. So to kind of, this stuff is these are kind of dry topics, really. So to make this a little bit more palatable, I think we'll frame this discussion rather than going over how our data worked at Domo, we'll kind of build up a hypothetical structure. So say we have a park. We're simulating a park as our service here. It has a bunch of trees in it. And it also has a bunch of raccoons. Because that's what I see when I go to the park. A bunch of trees and raccoons. And to add a little bit more layers to this, we'll say that all the trees and the raccoons, they all have a color and they all have an age. So now we have, our database that we are querying or something here. And so let's talk about first from our REST endpoint, what the URLs are going to look like. For our example here, I think it makes sense to write our URLs like this. You want access to the park and then the trees in the park or the raccoons in the park. And as a side note, I think it's actually it's good to use the plural form here, because then when you start, as you build upon this URL, I think the plural actually ends up working better. And so when we actually implement this, though, we're not going to implement a separate endpoint or controller for each different thing in the park, because as we add more and more, they can be different things. So we'll just abstract it away, saying this is what it'll actually look like internally. And so if somebody wants to request, raccoons, we can just parse out that, hey, let's actually query the raccoons. But if they want to get a little bit deeper and say, like, they want to filter out the data and say, we want all the raccoons that are the color blue. Let's say that they can add on a query parameter with a filter, and they can specify, hey, I want the blue raccoons as part of this query parameter. And the nice thing is that a lot of frameworks like Spring, which is what we use at Domo, it's what I'll use in our example here. We won't see much of the Spring part, but Spring can handle everything up to this point. It's at this point that we actually get into the grammar. How do we define that filter to say that a raccoon we want the blue raccoons or something? And a grammar, sometimes, for some reason, I feel like when we get into computer science, these words that normally are actually pretty simple and understandable, like they get kind of fuzzy and confusing. It's like, okay, what does a grammar actually mean? But I mean, I think it helps to go back to just what it means in the English language. A grammar is basically rules of how we build sentences and how you put them together, what order you put the words in. And if we share the same grammar, then we can understand each other. But the way that computer language grammars are a little bit different from human language grammars is that if you mess up your English grammar a little bit, the people can still get the gist. Whereas if you make one tiny mistake in your programming language, your compiler is just going to get mad at you because it has no idea what you're talking about. So anyway, back to building the grammar here. When I want to build a grammar, I really want to take it from the use case of the UI. What is the user going to want to naturally provide here? And kind of build our grammar from there. So let's say, for example, we wanted to query all of the trees that are red and less than 10 years old. So this, I think, might be a good way to do that. It's very readable, human readable, which is good for an API. Really the part of this that is defined by our grammar and not just handled by Spring is just this part in bold right there. So let's kind of work backwards from this specification and try to build out specific rules to define how our grammar actually works. So we can kind of break this statement up into two parts. You can see it's actually kind of a list. It's two different expressions. It's a list of expressions. So that's what I'm going to call them, at least. We'll call those expressions. We could call them whatever we want, really. And if we look at an expression closer, we can break it down into its constituent parts. This is what we're going to do. We're going to keep breaking this down until we get to, a basic building block that's the leaf node of our grammar, really. So we'll say that an expression is made up of a selector, which is kind of choosing the property of our raccoon or our tree or whatever, and then a comparator, which that's like the operation we're going to be applying to it, and then a value, which is pretty clear what that means. So we'll get down to the nitty-gritty here, where I chose in this case to define a selector. To me, a selector is kind of like a variable. So I chose some rules to define it like the same way that most rules follow in a lot of programming languages. It can start with a letter or an underscore, and it can contain letters, underscores, or numbers. And a comparator, for our examples, we're not really going to build out in a fully fledged query language. So we're just going to say you can check if something is equal to, which is less than, or greater than. And then for values, we actually have two different kinds of values. So in our example, we had red is one value, and then 10 years was a different value. So we're going to call the first one a simple value, and the second one a period value, because it's a value that defines a period of time. It could be 10 years, it could be 5 days or something. So the first one, for simple value, we'll just say that it's any number of lowercase letters. That's kind of restrictive, but in our use case, I think it'll work just fine, and it'll keep our examples simpler. And for our period value, we're going to break this into two different parts. You've got a number and a period. And you combine those two together to make a period value. So a number is really easy, one or more numerical digits. And then a period, we'll say it's either years, months, or days, one of those three. So now that we've kind of broken down that example API to break it into its constituent parts and make rules about what's allowed and what's not, we can actually piece those together a little bit more formally into a more formal grammar, and we'll be able to use that as a reference as we actually build out the code later. So we'll say that a filter, if you'll remember at the beginning, there was the query parameter filter. That's what the whole grammar is really about, is it's 0 or more expressions. So you don't actually have to include a filter, or you could include an empty filter, and we're not going to say that that's bad. Or you could have 1 or 2 or 3 different expressions that go with it. And an expression is a selector followed by a comparator followed by a value. I mean, this is what we've already seen. Our comparator is one of these 3 values, is less than or greater than. Our value is either a simple value or a period value. And then our period value is a number followed by a period. And a period can be years, months, or days. So this way it's all kind of a little bit more compact and in one place, and we'll be able to reference this as we go further on. So now this brings us to RegexParsers. We can actually implement this grammar now. And as you'll see, RegexParsers actually makes it really simple to just convert that grammar into code. And we'll be using some regular expressions. Are you familiar with regular expressions?
Yeah.
Okay, so we won't have to spend too much time on those, but RegexParsers works very well with regular expressions, as you can tell by the name. So we'll kind of zoom back a little bit, and remember, this is the part we have the filter string coming in from the user. It's going to go into our RegexParsers, which is going to output eventually an abstract syntax tree. So this is how you start out with building a RegexParsers object. And let's pull up our grammar that we wrote earlier so that we can reference that. And as you can tell, the grammar is actually kind of hierarchical. You have kind of a root node and then a bunch of leaf nodes down at the bottom. And so it's easier, I think, to define the leaf nodes first, since the other ones depend on them. So let's start out with defining our period at the very bottom. A period can be years, months, or days. And really, years itself is actually a node too. So we'll start with defining years. And what this does is we're creating a rule in our RegexParsers that says we're creating a parser called year, and it can be equal to the string years. And however, I actually want to change this a little bit because I'd like this to work whether or not the user includes the S, so that it's a little bit more human. And one way we could do that is by using the alternator and saying we accept years or year, but this is where regular expressions really come in handy. This is how in Scala you can write a regular expression. I think it's a really handy syntax. You do the triple quote followed by the .r, and it converts that string into a regular expression. However, this regular expression is still just equivalent to years. If we want to make the S optional, and you know how to do this, I'm sure, but here's kind of a table that shows some of our regex modifiers. If we just have years as is, it's an exact match. But if we put a question mark after the S, that means that the S, you can have 0 or 1 of them. A plus means you can have 1 or more S's, and a asterisk means you could have 0 or more S's. So in our case, we would want to match against year or years, which is equivalent to the question mark, the 0 or 1. So we'll just put a question mark in there, and now we have a regular expression that implements this grammar, this part of our grammar, that'll match both year and years. So month and day follow pretty similarly. They're like the exact same thing, really. So we can just put those on the board too. And now that we have those 3 things, we can define what a period is. So a period is either a year, a month, or a day. And if you're new to RegexParsers, you might look at this and be kind of confused because it looks like, day, month, and year are regular expressions, and now you're ORing regular expressions, and it's like, what does that even mean? And if you looked at a Scala regex class, it doesn't even have that operator implemented. So what's actually happening here is that RegexParsers, the parent class, converts the regular expression into a parser, which is capable of parsing a string as that regular expression. And so when we use that alternator, it's actually, that alternator operator is actually getting called on parser, which is a way of combining multiple parsers in an alternative fashion. So I don't really want to keep the types on there because I think it's really ugly, but that's what the type is when we're going to be looking at this. It's a parser of string. So let's move on. I think we can go a little bit quicker on this one, but this is how we would define a number. It's going to be one or more numerical digits. That's how we do that with regular expressions. And then finally, or now we can do period value. So here we use the tilde, which we used in our grammar, but in Scala, in RegexParsers, the tilde operator is combining two parsers. You have to have the first one followed by the second one. There's no kind of optional thing in between there. So that pretty much actually covers, the general concepts of how to start building a grammar in RegexParsers. So I'm going to jump forward a little bit and kind of implement a lot of the other rules of our grammar. We're going to jump forward all the way to selector. So a selector, if you'll remember, that's kind of like our variable, and it has to start with a letter or underscore and then contain letters and underscores or numbers. And I just wanted to talk about this one a little bit because the regex on it is a little bit more confusing. So in regular expressions, we can use these square brackets to indicate kind of a range of characters that are allowed. And as you can see on the table, you could say this is how you would show like lowercase, lower and upper, include numbers, not include numbers, underscores, and whatnot. And so for our selector grammar, we want to start with a letter or an underscore. So we can kind of do this piece by piece. We'd actually start with a letter and underscore this way, just including letters and underscores. And in order for it to start with a letter, that kind of necessarily means it has at least one. So the regex modifier for at least one or one or more is plus. So we put a plus on there. And then it can be followed by any number of letters, underscore, or numbers. So, but it doesn't have to. So that means we can have 0 or more, which is the asterisk operator. So that's really how we build out the selector. Once it's all together, it can look kind of confusing, but it's helpful, I think, to break it up into parts to understand where that comes from. So let's jump forward a little bit more. We're going to jump forward to our end object filter. And at first, it might seem to make sense to say that our filter is 0 or more expressions, but it's actually a little bit more nuanced than that, because we could have, one expression, color is red, or we could have 2 or 3, and we haven't really accounted for yet how do you put together multiples of these. Are they delimited by commas or spaces or what? So we can't just say expression star. And there's multiple ways to actually define a list of things, and I really like to break it down into parts. For me, it's easier to think about how do a lot of functional languages define lists, like Racket or Scala. A list is really one of two things. It's a value with the rest of the list, or it's a value and an empty list. Or it can actually just be an empty list as well. I didn't put that on here, but so let's kind of use that idea in our grammar. We'll say that a list is a head followed by a tail, where your head is going to just be an expression, and like color is red, and then the tail is going to be 0 or more of a comma followed by another expression. And And then to add on one more thing, it actually is okay if our list is just empty. And so a filter can be either nothing, or it can be a list that has a head and a tail. And once we have that, really, that actually completes our implementing our grammar in the regex parser. If we were to take that grammar that we defined and we put it all together, welcome.
Thank you. I thought things would be a little thin on Saturday.
Yeah.
Most classes look like this.
Yeah, it is pretty thin.
But parking was easy.
Yeah.
Yeah. Plus one for parking.
I know. I've got a lab later today, one of those like 3-hour long ones.
Oh yeah.
And I'm starting to wonder, like, it actually might be kind of nice if no one shows up. But so yeah. So what we're talking about here is building. Before you came in, we talked about building a grammar to define a query API. So I'll just do a really quick overview for you. So if we imagine we had our model, we were modeling a grassy park, and in it has a bunch of trees and a bunch of raccoons, and they all have a different color and a different age to them. And we want to build a RESTful API where we can say, give me all of the trees in the park that are red and under the age of 10 or something. And we had we decided to make our grammar look kind of like this. So the user would call this endpoint, calling in the park for all the trees, and they would filter down all of the trees using some expression saying color is red and age is less than 10 years. And from that, we built this is probably a pretty good overview to do anyway here. We built kind of an informal grammar. This isn't like following any sort of IEEE specification or anything, but it's just saying, hey, this is how we're going to break up that query into its constituent parts. Until we get down to the leaf nodes, the bottom. And now we just barely finished taking this grammar and actually building it out in Scala in a regex parser. And in the end, it looked like, let me pull up, find the end here. Yeah, here it was. So this is actually flipped upside down from the grammar. Our filter can be made up of a list, which a list is an expression. It's a list of expressions, really. And those expressions can be, like one expression is color is red, and it's all broken down into the code there. So how do we actually... now we have all the rules. This is kind of the rules in code, but how do we actually parse a string into some sort of object? And so say we have our method here. We want to parse our filter. We've gotten our string from our query. And we want to actually parse it. What do we use? If we look at RegexParsers, it has a method called parseAll, which takes a parser and a char sequence. So the filter that we just defined now, filter equals list ? So 0 or more lists. That's a parser. It is a parser object, so we can pass that in here. And our char sequence is that string that we pulled from the query, right there. The color is red, age is less than 10 years. So we'll go ahead and we'll use that, and we'll pass in our filter that we defined, and then the query parameter that we got from our user. But how do we actually tell, like, if it did anything? If we run this method, if we look at the return type of parseAll, it returns a parse result. And parse result is actually an abstract class that can be any one of these 3 outcomes. So in production, you want to handle filters that actually don't parse because of some sort of error or failure. But in this case, we're just going to look at filters that actually succeed for simplicity's sake. So we'll just be focusing on success. This is how the cat class success is defined. It's just a case class. So all it has is the result, which is of type T, and then next. We can just ignore next for now, but look at, we'll pull result out of our success object. So this is what we do. We call parse all, we pattern match it, and we pull out result. And let's go ahead and look and see what this call would look like. Oh yeah, that'd be great. So say we'll call our parse filter method and pass it some different things. If we pass it the empty string, which is totally valid, if they're not filtering on anything, then we get none. That's pretty sensible output. But if we pass in color is red, it's kind of interesting what we get back. So we get some to indicate, that we had a successful parse here. And it's kind of hard to really see what is in sum. So let me kind of break it out for you. It's a list of tuples, right? Not a list of tuples. It's a single tuple that is a tree tuple. Yeah, a binary tree, I guess. So now this hierarchy here actually matches exactly what we defined in our grammar. And you can map all of these nodes back to their grammar counterpart like this. And the only problem is that this structure that we have right here, that is the output, is just, it's a bunch of tuples. And when we look at it, when we look at the group that contains the phrase color is red, we don't actually know programmatically like which is the selector, which one is the comparator, which is the value. It's just nodes with no semantic meaning to them at all. We could refer back to our tree and kind of go back and forth and figure out, oh, okay, color, that was the selector part of the tree, and that was the comparator. But what we would really like is actually just a combination of the two, just put them together. And this is what is called an abstract syntax tree. If you haven't dealt with abstract syntax trees, that's all it is it's putting semantics into that hierarchical parsing tree. So
I can't ever say that right.
Yeah, AST is what I'll probably call it for the rest of the talk. It's a lot easier than abstract syntax tree. Hierarchical, yeah. So let's actually build the abstract syntax tree. So we'll be creating, before we actually can build before we can actually get our regex parser to build an abstract syntax tree, we need to build the model of that tree first. So again, we're going to reference our grammar, and we're just going to build a bunch of case classes that just represent our grammar. That can give some semantics to it. So we'll start with period, and a period can be years, months, or days. I think that's a great opportunity to use an enumeration. And then we have our different values. We have our simple value is just a string. Oh, you know what? There's a mistake here in mine. Do this. I think this was just like this. I think that is what it's supposed to look like. But so if you look at how we define expression, it's a selector, a comparator, and a value. But a value can be one of two different implementations. So we're going to have a class value, and we're going to just extend it, and it can be a period or a simple value. That way we can kind of use that sort of object-oriented programming there too. I forgot the word for that. Polymorphism. So we can treat period values and simple values the same in our grammar. A comparator, that's also we'll just make it an enumeration. It can be one of those three values, is, less than, or greater than. And then our expression, which is an expression has a selector, comparator, and a value. And then finally, our filter, which is a list of expressions. So So there we go. These are all really simple. They're case classes, no logic. They're just models, really. And so if we have our grammar right here, and we have our syntax tree, that we built, all those case classes, what we want to do is we want to combine them to get our completed abstract syntax tree. And fortunately, RegexParsers makes this so easy and so simple. You can just inline your tree directly into your grammar. So let me show you. For example, if we have our period here, you can use this triple caret operator, and if we parse a part of our filter to be the object day, we can actually just return that enumeration, the period day. You can just return it directly. And that way you're actually meshing together your grammar and the syntax tree together. You can look at them like side by side. It's so easy and easy to use. And so the value here, what RegexParsers is going to do is when you return period.day for that first example, it's actually going to package that into a parser. And so that's what that triple caret is going to do. It's going to take that value you supply and put it into a parser that returns a period.day. So there we go. So we can just kind of go through our grammar. In most cases, doing this is pretty simple. But like some here, like our number, we actually, when we're building our period value, we need our number to be an int, whereas in our parser, it's really just a string that's representing an integer. So in this case, if we actually need to change or modify what we've received a little bit, we can use the double caret notation, and it takes the string that it parsed, and then you can actually do something to it. In this case, we'll just convert it to an int. And now we'll be able to get an int out of that. And if, for example, the user who's using our API doesn't actually send you an int, it'll just fail right here saying, you actually just didn't even send us a valid syntax, valid grammar. And you can provide error messages that reflect that rather than just saying, hey, you broke it. You can say, hey, this is the specific part of your query that didn't really match up and didn't work. So that's how the double caret notation works. Let's go here to our next item. So here when we're using that tilde, we can actually still use that double caret notation, and you can take both of those values, the number and the period, and you can just put them together using those case classes we built. So most of them are pretty similar to that, but I want to jump forward to building our list, because our list is a little bit more of a complex object right here, especially the tail. When you look at that, how we define tail there as any 0 or more comma expression tuples. Something, I don't know if you guys knew this. Do you guys use Eclipse or IntelliJ or something else?
Eclipse.
Use Eclipse?
Emacs.
Emacs? Okay. So I don't know if you can get this in Emacs somehow. There's probably a plugin somewhere. But in Eclipse, if you just hover, if you wrote this code exactly as is and you hover over something, it'll actually tell you the type that something is. In IntelliJ, there's like a key combo you have to press. But it would show you that this is really helpful, because like when I wrote this, I'm like, okay, I actually don't even know what I'm getting here as something. But it's a list of these tilde combined objects, which really, if you look in the documentation, it's just a tuple. So you have a list of tuples, which are a string and an expression. The string is actually the comma that we're matching against. We don't even really care about that comma. It's just there for the user. So what we'll do in this case is we're going to map out all of the expressions and just discard the commas. So if we just take the list object and we just map everything to the expression, it just kind of discards all the commas. And then creating the list given the head and the tail. That's just consing those two together to build the list. And running out of time here, so we'll go really quick here to the end, and then you guys can ask any questions you might have. But this is how you build the filter. It either has a list or it doesn't. And so in our case, I wanted to, if they didn't provide anything, I just wanted to return an empty list. So this is how I did that. So we'll just do a quick demo of this if we want. I will run this on this side. So here's our filter parser class. It has all those rules that we built into it, and I'm just going to run it. I'll just show you real quickly here the controller. It's going to take this filter value that the user provides, and it's going to run it through our filter parser, and then it's just going to convert the output to a string. So we'll see that abstract syntax tree. It'll just be in string output form, really. There's my mouse. Localhost. Let's move this onto the other screen so you guys can see. So local host :8080 park. So let's try running this query right here. So what we're saying is we want all of the trees where their color is red and they're less than 10 years old. And it's not available. Oh, because I had some sort of error.
Always the first page I get too.
Yeah. Let's see here. I think we just need to rerun this great old build. I know this is the law of demos, right? So they don't actually work. There we go. Go Spring. Okay, let's just run that one more time here. And we get it. Let's see if we can make this a little bit bigger. I can zoom in, but it doesn't actually change the size of the text. Let's just copy that and put it in text edit, and then we can see it better. Where's my mouse? There it is. Okay, so it gives us back our fully built abstract syntax tree. So now we know that when we say color is red, we know that color is this first parameter in expression, and is the second parameter, and red is a simple value, and we have age less than 10 years, and you can see how the string input that the user provided is combined with the semantics of those case classes that we built. And what you can do from here is it's really easy using the visitor pattern or any other way that you really want to code it to go through this list and actually convert this kind of an expression to SQL, or in our case it was our own internal data request API. And now you've kind of built that abstraction layer on top of whatever internal mechanism you have, and you can have that direct control over what your users are using and what they're seeing. And yeah, and there we go. That is it. There's let me just pull up the slides again here, but there's that link there on the bottom. These slides are available on the joined in if you later wanted to go back and refer to that code and see how everything works. And I've got all the code hosted there at coryklein.com/openwest. So, any questions? Yeah, it's kind of fun because when I built it, you get to it's kind of like building actually a programming language, because that's the same process you go through with grammars and syntax trees and stuff. And you realize, hey, actually building a RESTful API is a programming language. you're building your own little mini programming language. And so it was kind of a fun way to actually do that directly. So.
And you're using this as a production app?
Yep. Yeah, we're using this in production at Domo. So.
I went to school here at UVU and we had to do a compiler for some language that our teacher gave us that just made up, right?
Yeah.
So I had to do that manually. So we couldn't use any like parser libraries or whatever. So but that's really handy.
Yeah, I really think it is just amazing that almost the entire language, the spec for that, is just right here.
Yeah.
You know, Scala is so compact and clear about it, so it's really great. Scala is a great tool if you wanna get into that kind of thing. So, okay, well, thanks guys. Glad you could come.
Thanks.
Yeah.